When you cut to the bottom line, there's one thing all these vehicles have in common. They're all designed to convert explosive energy into controlled motion. The transmission is the mechanical link, which transfers the engine's power to the wheels. But it's the driver who controls the power. To get maximum speed, performance, or pulling power, a good driver knows the vehicle and its handling characteristics. But more important, he's trained how to drive. And you learn that it's not how fast you drive that wins the race, but how well you drive. So what does learning to drive a race car have to do with repairing a transmission? Well, in both cases, you're interested in developing speed. As in racing, you first have to be sure you have the basics if you expect to be very fast at repairing a transmission. That's where this training course comes in. We'll cover the techniques for noise diagnosis and shift concern diagnosis. Then look at clutch repair, transmission and transaxle repair, and transfer case repair. In our first topic, noise diagnosis, we're going to focus on when the noise occurs rather than what the noise sounds like. Here's an example of a noise that occurs only while the clutch pedal is being pressed or released. The obvious components to check are the clutch pedal pivot bushing and other clutch actuation components. If you find no problem there, you should also check the input shaft quill that the release bearing slides on. Look for lubrication, scoring, or alignment problems. Another possible noise symptom you may encounter is one that occurs only when the clutch pedal is fully depressed. One possible cause is the release bearing, since it's under load when the clutch pedal is held in. Another possibility is the pilot bearing. When the clutch is engaged, the clutch disc is clamped between the flywheel and pressure plate, and the input shaft turns at crankshaft speed. When the clutch is disengaged, the input shaft slows to a speed slower than crankshaft speed and rotates within the pilot bearing. If the bearing has failed, this will probably result in more noise. Now, let's say you have a high-pitched squealing noise at idle with the clutch engaged. Begin by testing for possible clutch-related causes. A noise at idle could be caused by insufficient release bearing preload or pressure plate release fingers that are worn or uneven. You can isolate these possible problems by pressing the clutch pedal part way to put load on the release bearing. If the noise goes away, it's an indication of a problem with the release bearing preload or pressure plate fingers. If the noise gets louder when the release bearing is loaded, it's likely a release bearing problem. If there's no change in the noise, then it's probably in the transmission. The next test you can perform is to press the clutch pedal all the way in. If the noise goes away when the clutch is completely disengaged, then you can suspect the problem is in the transmission, not the clutch. Several things may cause transmission noise at idle when in neutral: input or counter shaft bearings, output shaft pilot bearing, the input shaft and counter shaft drive gears, or neutral gear rollover. When the gears are not under load at idle, the loose meshing of the gear teeth causes neutral gear rollover. The noise may be more pronounced in heavy-duty transmissions and transaxles. With the clutch engaged and the transmission in neutral, you can isolate gear rollover by increasing the engine RPM. If the noise goes away when engine RPM is increased, it's probably rollover noise. Make no attempt to repair the transmission. This is a normal condition and cannot be repaired. If the noise continues or increases when engine RPMs are increased, then you may have bearing or drive gear problems. To isolate the problem, you'll need to perform a test drive. In your test drive, accelerate and decelerate through all gears. If the noise goes away in fourth gear, the problem may be in the output shaft pilot bearing. This bearing is under load whenever the input shaft and output shaft are turning at different speeds. But in fourth gear, the two shafts are splined together and rotate at the same speed, taking the load off the output shaft pilot bearing. If the noise goes away in fourth gear, it may also be related to the input shaft and counter shaft drive gears. These gears are also not under load when the input and output shafts are splined together in fourth. If the noise only occurs during acceleration or only during deceleration in all gears except fourth, it could indicate damage to the drive side or the coast side of the input shaft or counter shaft drive gears. If the noise is relatively constant in all gears, it may be the input shaft bearing or one of the counter shaft bearings. Press the clutch pedal and put the transmission in neutral. While coasting at highway speed, see if the noise goes away when the input and counter shafts stop rotating. If you have a noise that occurs only while driving, and it occurs in all gears, it may be the output shaft bearing. Be sure to eliminate wheel bearing, axle, and driveline as possible causes before disassembling the transmission. Gear noises are usually the easiest to identify. They normally occur only while driving in that gear and will be most pronounced either while accelerating or while decelerating, depending which side of the gear is affected. Carefully inspect the corresponding gears on both the output shaft and counter shaft. After your test drive, be sure to check the transmission fluid. Dark or dirty fluid may indicate bearing wear. If the fluid is clear, check for fine metal particles sticking to the magnet on the drain plug, which could be a sign of gear damage. Let's take a moment to review the principles of noise diagnosis for typical 5-speed transmissions. Most bearing noises are described as rough or rumbling. Gear noises usually have a higher pitch and are described as howling or whining. Most transmission gear noises are also not present until the vehicle is in motion. The one exception to this is the input and countershaft drive gears. If the noise is present in neutral as well as all gears and follows engine RPM, not road speed, the probability is either the bearings or the drive gears are worn. Wear or damage to a speed gear pair will usually make noise only when the transmission is shifted into that gear, and the noise will follow road speed. Except for input shaft drive gears, gear noise is normally affected by the rotational speed and loads on the transmission output shaft. The output shaft bearing is also affected by road rather than engine speed. Gear noises usually change and may disappear entirely when the vehicle is coasting or decelerating. In most instances, the gear noise will have a definite quality of sound difference between acceleration and deceleration. So far, we've examined the conventional clutch transmission configuration used in many Ford cars and trucks. But Ford also manufactures several front-engine, front-wheel drive models, such as the Escort and the Tracer. They combine the transmission and the differential into one unit, the transaxle. The causes of noise in a transaxle are similar to those in transmissions. However, the components are slightly different. One major difference is that the transaxle does not have a countershaft. The second major difference is that the differential is incorporated into the transaxle, adding several components which could contribute to noise symptoms. Another noteworthy difference with this transaxle is that tapered roller bearings replace some ball and roller bearings. These are found on the input and main shafts as well as in the differential. Tapered roller bearings require precise preloading to set proper compression between the bearing rollers and the race. If the noise symptom is directly related to road speed, regardless of engine speed or clutch engagement, your best conclusion is a problem in the differential, since the differential turns at all times while the vehicle is in motion. In this case, the noise would continue when the car coasts to neutral and usually quiets when the car decelerates. If the noise doesn't change during a turn, you can rule out wheel bearings or half shafts. Focus on inspecting the differential for wear or damage. Lack of lubrication, contaminated fluid, aggressive driving, and driver error are the major reasons that transmissions come to you for repair. Another reason is excessive loads leading to premature wear or component failure. Our final comments on transmission noise diagnosis deals with the transfer case. In 4x4 vehicles, you'll be faced not only with isolating noise concerns to either the transmission or clutch, but also between transmission and transfer case. When examining the transfer case for a bearing or gear noise, consider all the facts. If the noise only occurs in four-wheel drive, that eliminates the clutch and transmission, as well as the input and rear output shaft bearings. A bearing problem may leave signs of its failure in the fluid. If the fluid is clear, the problem is probably not a bearing, but more likely a gear. Be sure to check the fluid for fine metal particles, as this could be a sign of gear damage. For a noise that occurs only in four-wheel drive, the chain is a very likely suspect, since it's always turning when the transfer case is in four-wheel drive. A stretched or damaged chain would make noise anytime the front output shaft turns. We'll look more closely at transfer cases in the final segment of this tape. In this topic, we've covered clutch, transmission, transaxle, and transfer case noises, in much the way you'd see them coming into your own service area. But now we're going to switch from noise concerns to shift concerns. Professional drivers don't work alone. They're backed up by some of the fastest and best technicians in the business. As a team, they race their real opponent, time. During a race, time is everything. And when you're repairing a customer's car in your shop, time is important too. But you have to be careful of shortcuts, because some shortcuts actually end up costing you time, such as not doing thorough in-vehicle tests before disassembling the transmission. Before you open the case, you better have a good understanding of the symptoms and a clear idea of what you're looking for. The common shift concerns with manual transmissions, transaxles, and four-wheel drive transfer cases are hard to shift into gear, stuck in a gear, jumps out of gear, can't shift into a specific gear, or gear clash when shifting. Diagnosing and repairing these kinds of shift problems goes much faster when you have a keen understanding of how all the components related to shifting work and the symptoms created when they fail. For instance, you can get shifting problems because of incomplete clutch disengagement, shift linkage wear or damage, or worn synchronizer components. When diagnosing shift concerns, you'll frequently encounter one-of-a-kind problems you've never seen before. Since it's impossible to establish a cause and effect relationship for every possible problem, you'll have to rely on your understanding of how the shift components work to know where to start looking for the cause. In this topic, we'll start with shift levers, rails, and forks. Next, we'll focus on synchronizer operation and then the unique aspects of reverse gear operation. Finally, we'll have a look at the role proper clutch operation plays in shift concern problems. Let's start with the shift mechanisms. Assume we're dealing with a rear-wheel drive 5-speed transmission, such as the M50D used in F-Series trucks. Problems with the shifting components are a likely source of these shift concerns, but not the only possible source. You should check the shift mechanisms first, however, because they'll usually be easier to get to and repair. The shift mechanisms for this M50D 5-speed, for example, include the shift lever, the shift boot, the shift rails, and the shift forks. One problem you might encounter with the shift lever is improper clearance between the lever and the console. This may prevent completely shifting into one or more gears, usually third and fifth, and can lead to complaints of jumping out of gear or not shifting into a gear. The shift boot can also be the source of shift concerns. A stiff or improperly installed shift boot can make the transmission jump out of gear. Shift rails can have a variety of things go wrong, resulting in different kinds of shift concerns. Loose or improperly installed parts can restrict shift rail travel and cause a transmission to not shift into one particular gear or to lock into one gear and not shift at all. Restricted travel can also prevent the synchronizer from fully engaging a gear and create jump-out problems. Also, examine shift rails closely for scoring. Scratches caused by debris from failed parts can interfere with shift rail travel in the bores. Even the slightest extra resistance can lead to hard shifting problems. Bent or misaligned shift rails might also shift hard, or won't shift into one gear, or lock in a particular gear. A spring-loaded detent mechanism holds the rails into the selected gear position until force is applied during shifting. If the detent mechanism is not functioning properly because of worn, missing, or improperly installed springs and balls, the transmission will have a tendency to jump out of gear. Remember that the gears affected will be limited to the shift rail, which has the problem. Shift fork problems such as a loose fork on the shift rail, a bent fork, or worn shift fork pads can prevent the synchronizer from fully engaging its selected gear. The transmission may jump out of gear or clash gears during shifting or lock in one gear. But if the problem is not in the shift components, the next place you might look is the synchronizer assemblies. Let's look at how the synchronizer is supposed to work, then look at the symptoms related to synchronizer problems. This is a synchronizer assembly that's typical of what you'll find in most transmissions and transaxles. The parts of the synchronizer assembly are the clutch hub, the coupling sleeve, the synchronizer rings, the insert keys, and the insert key retainer spring. Let's look at each component one at a time. Each synchronizer assembly has a coupling sleeve that slides on the clutch hub. The teeth on the inner circumference of the sleeve mate with the teeth on the outer side of the clutch hub. To prevent shifting problems, the coupling sleeve must slide smoothly on the clutch hub. Once the synchronizer body is disassembled, to test the sleeve, lift it about 3/4 of the way off the hub and release it. The sleeve should slide downward over the hub on its own without any additional force. If it requires a push, the sleeve may be binding and should be serviced. A binding condition could be caused by debris scoring the surfaces between the sleeve and clutch hub or by damaged insert keys. If you find evidence of scoring, inspect the transmission closely for damaged or nicked gears or failed bearings to find the source of the debris. The coupling sleeve must also travel far enough to fully engage the speed gears on either side. Jump-out problems can occur if anything prevents the sleeve from traveling the full distance to completely engage the gear. When inspecting a transmission, always check for excessive shift fork pad wear by measuring the clearance between the shift fork and the rim of the coupling sleeve with a feeler gauge. The clearance should not exceed the specifications in the shop manual. The synchronizer ring has a beveled inner cone that mates with a similar cone surface on the drive gear. The synchronizer ring's cone surface is machine grooved to provide a gripping action when it's forced into contact with the drive gear. The gripping action of the synchronizer ring as it's forced onto the drive gear during a shift brings the drive gear up to the same rotational speed as the clutch hub and sleeve. When the drive gear and clutch hub are rotating at the same speeds, the sleeve can easily mate with the drive gear without clashing, providing the synchronized shifting feature. If the inner gripping surface of the synchronizer ring is worn, it won't bring the drive gear up to the same rotational speed as the sleeve, and gear clash will occur. You don't have to disassemble a synchronizer to check for synchro ring wear. You can simply measure the clearance between the synchronizer ring and the drive gear when they're firmly in contact with one another. A measurement less than that listed in the shop manual is a sign of excessive wear. The synchronizer ring also has beveled points on its teeth that match the beveled indents inside the coupling sleeve. These points assist in aligning the synchro ring with the coupling sleeve. If the teeth on the synchro ring are rounded by wear, it could take noticeably more force to slide the sleeve over the synchronizer ring teeth and make it difficult to shift into one specific gear related to that synchronizer ring. Improperly installed or damaged insert keys can interfere with coupling sleeve movement, causing hard-to-shift, locked-in gear, or won't-shift problems. It can also create uneven pressure on the synchronizer ring, which then fails to adequately grip the drive gear, causing gear clash when shifting. The insert keys are held in place by the retainer springs. Installing the springs in the wrong direction, or in some transmission models, such as the M5R2, installing opposing springs in the same direction can create shifting problems. Springs should also be inspected for proper tension. We've covered shift mechanisms and synchronizers in general because they pretty much work the same for all forward gears. But reverse gear is another matter. Now we're going to look at reverse gear and its unique operation as related to shift concern diagnosis. Transmissions have used two very different approaches to reverse gear shifting. One approach uses a synchronizer and coupling sleeve, just as for all the forward gears. This is typical in the M50D, M5R2, and S542ZF. The other method of engaging reverse gear does not use a synchronizer. In this T50D transmission used in the Mustang, reverse is engaged by a movable idler gear, which slides into contact with spur gears on the countershaft and output shaft. A movable reverse idler gear is also typically used for reverse shifting in transaxles. One unique feature of the T50D is that the spur gear on the output shaft is actually part of the synchronizer sleeve. Since there's no synchronizer to prevent gear clash, any rotation of the input or output shafts during a reverse shift will cause a grinding noise. Therefore, for this and other transmissions, without reverse gear synchronization, gear clash in reverse is usually a sign of a clutch disengagement problem, or not coming to a complete stop before shifting into reverse. In either the synchronized or non-synchronized arrangement, reverse shifting problems can be caused by the shift mechanisms themselves, the shifter, rails, forks, and levers. In those transmissions having a reverse synchronizer, shift concerns can have the same synchronizer-related causes as the forward gears. Of course, not all shift concerns originate in the transmission. One of the most important considerations in shift concern diagnosis is verifying proper clutch operation. The purpose of the clutch is to disconnect the engine from the transmission input shaft, so the synchronizers can bring the drive gears up to the same speed as the output shaft during a shift. If the clutch doesn't fully disengage the engine from the transmission components, then you're going to get shifting problems. It's fairly easy to tell when a gear clash or shift problem is clutch-related. The single most convincing symptom of a clutch-related shift problem is that it occurs in all gears. If the suspected cause is clutch-related, check release bearing travel. If the bearing travel is less than 7.5 millimeters, the hydraulic system may be leaking. If the clutch travel seems fine, consider other possible clutch problems, such as pilot bearing binding, housings or shafts out of alignment, clutch disc binding on input shaft splines, and any other factor contributing to incomplete clutch disengagement. We've covered noise and shift concern diagnosis. Well, now let's move on to repair. Winning drivers learn to master three things: throttle, clutch, and shift lever. The throttle and shift lever control the engine and vehicle speed, but it's the driver's skill with the clutch that brings the two together. The clutch is the link between the rotational power of the engine and the gears in the transmission. Now, since the transmission depends on the clutch for its power, some problems that seem to be in the transmission may actually be in the clutch. In this section, we'll look at cable clutch controls, followed by a detailed look at hydraulic clutch controls. Then we'll cover the inspection of clutch components, including the release bearing, pressure plate, clutch disc, and pilot bearing. Let's begin with cable clutch controls. With a cable clutch system, like the one on this Mustang, you may find problems with a sticking or non-releasing clutch. Typically, the customer concern will be that the clutch pedal is hard to press or the vehicle is hard to shift. In most cases, the feel of the pedal will tip you off that there is a clutch linkage problem. To be sure that it's not a cable problem, you should disconnect the clutch cable at the release arm. If the clutch control cable still sticks, the problem must be in the clutch controls. Now, test the cable by pulling it back and forth from the release arm end. The clutch cable should move with almost no effort at all. Modern cables are pre-lubricated at the factory and shouldn't need lubrication in the field, but there are two common reasons that a cable might stick. The cable can become frayed, like this one, or it can become kinked if it's misrouted. Once the cable has been kinked, it can't be reused. When installing a new clutch cable, carefully follow the routing instructions in the manual. Once the cable is installed, the Mustang cable clutch control system is self-adjusting. Just lift the clutch pedal away from the floor for initial adjustment, and the mechanism will continually self-adjust from then on. While the cable clutch control system is still used on the Mustang, many current Ford vehicles use hydraulic clutch controls. The hydraulic clutch system transmits the motion of the clutch pedal to a remote or slave cylinder using hydraulic pressure. When the master cylinder push rod is forced into the master cylinder, the fluid in the main chamber is forced out through the hydraulic line. This line terminates at the slave cylinder. There, the fluid fills the slave cylinder pressure chamber and forces the slave cylinder outward. This presses the release bearing against the release fingers of the pressure plate and disengages the clutch. The entire system depends on the containment of fluid pressure to do its job. A leak in the hydraulic lines can introduce air into the system and limit the amount of pressure that the master cylinder can deliver to the slave. If there's air in the hydraulic lines, pressure from the clutch pedal compresses the air instead of forcing the fluid into the slave cylinder. The clutch may only partially disengage, depending on how much air is in the hydraulic lines. Either of these problems can prevent the clutch from fully disengaging when the pedal is depressed. The hydraulic clutch system will lose a small amount of fluid over time. Any fluid that's lost must be replenished if the system is to continue to operate correctly. The master cylinder reservoir holds the extra fluid that the system needs in reserve. When the system is low, it automatically replenishes itself through a small hole in the bottom of the chamber. When the clutch pedal is at rest, this small hole, called the recuperation orifice, is open. Fluid can then flow freely back and forth between the master cylinder reservoir and the master cylinder pressure chamber. When the clutch pedal is depressed, the master cylinder diaphragm slides forward, blocking the orifice and allowing pressure to build up in the hydraulic lines. When it's released, the push rod and diaphragm slide back, re-exposing the orifice and allowing the system to be replenished. This opening also serves to equalize the pressure in the system. When the orifice is open, the hydraulic fluid can freely expand and contract by flowing through the orifice and into the reservoir and deforming the soft diaphragm inside the reservoir cap. When the system heats up, the total fluid volume increases, but the excess volume of fluid exits through the recuperation orifice. The amount of compressible fluid in the hydraulic lines remains the same, so that the slave cylinder stroke is always the proper length for correct actuation of the clutch. If the recuperation orifice becomes blocked, the system will not be able to equalize. Instead of surging back into the reservoir, fluid is trapped inside the pressure chamber. When the vehicle heats up, the fluid expands, forcing the slave cylinder outward, partially actuating the clutch. Anything which prevents the master cylinder diaphragm from recovering to its correct position or prevents the reservoir expansion diaphragm from properly contracting can cause the clutch to partially disengage by itself. Now that we have a better understanding of hydraulic clutch controls, let's move on to the inspection of other components of the clutch system, starting with the release bearing. The release bearing presses against the release fingers of the pressure plate and disengages the driven disc from the flywheel. It must move an adequate distance to completely release the disc. The exact distance it must move varies from vehicle to vehicle and is listed in the Vehicle Shop Manual. If the hydraulic clutch system can't develop adequate pressure, bearing travel will be less than the specified amount and the clutch will not fully disengage. This can cause gear clash or a hard shift problem. To test the release bearing, first remove it from the slave cylinder. Rotate the bearing while putting slight pressure on the outer race. It should turn smoothly. Check the inside of the bearing and the input shaft quill where it rides for burrs. The quill is smooth, but there's some minor roughness on the inside surface of the bearing. In this case, either polishing or replacing the bearing would be acceptable. Of course, if there is extensive damage to the inside of the bearing, it should always be replaced. Next, inspect the pressure plate. The pressure plate clamps the clutch disc to the flywheel, transferring the engine's power through the disc to the input shaft of the transmission. When the release bearing presses against the release fingers on the pressure plate, the clamping pressure is removed, disengaging the clutch. It's important to check for release fingers wear. If the fingers are worn, the clutch may not fully release. Be sure to inspect the face of the pressure plate to see if it's been burned or worn. Now let's check the clutch disc wear. To check clutch disc wear, you need to inspect the wear lines built into the disc. They fan out from the center and can show wear across the disc's entire surface or indicate wear patterns where the disc is wearing selectively on one side, possibly indicating a housing alignment problem. These wear lines indicate the disc was badly worn. Finally, check the pilot bearing. The end of the input shaft is held in place by the pilot bearing. which allows the flywheel and the input shaft to turn at different speeds during shifting, but still maintains proper alignment. It's important that the pilot bearing operates smoothly at high speeds, otherwise the bearing may be noisy. It could also allow the input shaft to move out of alignment. It's best to check the pilot bearings in place because once they're removed, they must be replaced. These bearing rollers look okay. They're rotating smoothly and the bearing is firmly seated. The inner race on the input shaft is also undamaged. There's no problem here. Once the major components have been inspected and replaced if necessary, the clutch can be reassembled and reinstalled. Good work. You can save time and earn better money by isolating transmission problems right away. Checking the clutch controls and the clutch is an important part of that process. It's best not to break open the gearbox unless you need to. In the next topic, we'll take a look at what happens when you do need to. Performance driving, a good driver develops an inner sense of the exact moment to shift to get the best gear ratio with the minimum loss of momentum. But the sudden changes in loading and gear speeds puts an incredible strain on the bearings, the gears, the synchronizers, and the shift rails. And in these cars, the slightest miscalculation can be disastrous on a transmission. Well, you may not be working on too many transmissions that have been trashed on a racetrack, but you will be faced with problems caused by driver mistakes, such as shifting without fully depressing the clutch, or problems simply caused by high mileage or low fluid. Now in this topic, we're going to get into transmissions and transaxles, literally piece by piece, and learn what it takes to get them back on the road again. Before removing a transmission or transaxle, take note of the following. Be sure you've performed all in-vehicle tests, and be sure you've looked through the shop manual to identify all special tools and special procedures required. When you begin disassembly, you'll find the general procedures are similar for most models. Let's use an M50D rear-wheel drive transmission found in many F-Series trucks as an example to illustrate these common procedures. Note that transmissions or transaxles with aluminum magnesium cases can be easily damaged by prying. Use a plastic-tipped mallet to loosen these cases instead. Pry carefully at the pry bosses to avoid damaging the mating surfaces, which can cause transmission leaks. When it's necessary to lock the transmission output shaft to keep it from rotating during removal of the lock nut, simply slide the 1-2 synchronizer and the 3-4 synchronizer onto the first and third gears. Unstake the bearing retaining nuts with a small chisel. Remove the counter shaft and output shaft rear bearings first, followed by the reverse idler, reverse gear, and fifth gear assemblies. After removing the front and center bearing covers, you have access to the main assemblies. Don't take a sub-assembly apart unless you find a problem or closer inspection is required. If an inspection is necessary, the major components that should be checked are bearings, synchronizer assemblies, gears, shift forks, and the transmission case. In the following examples of inspection procedures, the T50D transmission used in Mustangs will be inspected. Begin by inspecting the bearings. Clean and lube the bearing, then spin the outer ring by hand. If roughness or vibration is noticeable, the bearing should be replaced. Examine the bearing for cracks in the bearing cage or damage to the inner and outer races. Light particle indentation on the races is okay, but heavy indentations or any sign of spalling, where small bits of metal have actually been pulled off the surface of the race, are unacceptable. Begin inspection of synchronizer assemblies by visually inspecting for signs of wear at the shift fork contact surfaces. Inspect the synchronizer ring for rounded clutch teeth or a widened index slot. Check for blocking ring wear by measuring the distance between the face of the ring and the face of the gear and comparing to specifications in the shop manual. If the gap is too narrow, it's a sign of unacceptable wear. Finally, check the synchronizer sleeve for free movement on the hub. Always take note of alignment marks. Since the T50D doesn't have alignment marks on the synchro assemblies, you would paint marks on the ring and coupling sleeve before disassembly. When inspecting gears, you should look for tooling or grind marks on the drive side of the gear, chips or nicks on teeth, and abnormal contact patterns. Tooling or factory repair grind marks on tooth surfaces are normal, but chips or nicks in teeth or abnormal contact patterns should be examined closely to see if they're within acceptable limits. Any abnormal pattern indicates the gear is not meshing correctly. Make sure the pattern doesn't extend off the face of the gear tooth and that the pattern is not unusually small. Occasionally, you'll find a gear tooth with a small chip or nick. When the chip or nick does not extend into the contact pattern or extends into the contact pattern only from the top, or does not extend from the side of the tooth into the face, it's acceptable to smooth the nick or chip by grinding and reuse the gear. In some cases, particularly synchronizers, you'll need to disassemble the components on the output shaft for closer inspection or replacement. We'll go through the steps involved in disassembling the output shaft on the M50D. The procedure is almost identical to the M5R2. The front flange separates the front or short side of the shaft from the rear or long side of the shaft. Use it as a reference point. You'll remove the components on the short side first: the output shaft pilot bearing, snap ring, needle bearing, and spacer. Next, remove the third, fourth clutch hub and sleeve assembly, the third synchronizer blocker ring, third gear, and needle bearing as a unit. If the synchronizer assemblies are removed, keep the blocking rings with their original assemblies. Since they've established wear patterns, moving them to a different position could accelerate wear. Now, disassemble the long side of the shaft with the press. When using the press, make sure the flange does not contact the press cradle. The components on the long side of the flange are pressed off as a unit: the center bearing, first gear sleeve, first gear, needle bearing, first-second synchronizer, first-second synchronizer ring, and needle bearing. Once the output shaft is disassembled, a closer inspection of the synchronizer assemblies can be performed. Here's an example of a worn synchronizer ring. The inside grooves are worn smooth, and the ring won't grip the gear cone. You'll definitely need to replace the ring. Now inspect the rest of the synchronizer assembly to see if it has any other problems. Check the keys, the inner surface of the sleeve, and the insert grooves for wear. Also, inspect the insert spring for tension. Looks like only the ring will need to be replaced. To reassemble the synchronizer, align the new synchronizer rings with the insert keys on the hub. Make sure the reference mark faces the rear of the transmission. Reassemble the long side, making sure to lubricate all rotating or sliding parts with Mercon as you do. Then, install the short side components. Check the clutch hub end play using a feeler gauge. If the measurement is not within specification, obtain the proper thickness retaining ring and install it. Now, the sub-assemblies can be reinstalled and the transmission reassembled. Most often, it's not enough to just inspect and replace parts. You'll also need to check preload and end play. In the following example, we'll be using an S542ZF transmission used in F-Series trucks. Generally, whenever a component is replaced that affects the length of a subassembly, you need to do a preload adjustment. Refer to your shop manual for specific information. Many transmission cases are made of an aluminum-magnesium alloy. Most subassemblies are made of steel. These metals expand at different rates. Preload adjustment compensates for the difference in expansion rates. Preloading the shafts makes sure the bearings fit correctly when the unit reaches operating temperature. Acceptable preload varies between a minimum and maximum. To adjust preload, shims are used to establish precise overall shaft lengths. Inadequate preload will allow the shafts to move and may cause the bearing races to spin in the case, resulting in noise and component damage. Too much preload may cause the bearing to overheat, resulting in noise and premature wear. Let's walk through a preload adjustment on the main and input shaft of a S542ZF transmission. Remember, this is just an example. Each and every transmission and transaxle is different. In many cases, the first step is to remove the old shim so that you can get a baseline measurement. It may be necessary to use a slide hammer and puller to remove the counter shaft and input shaft tapered roller bearing outer races. In some transmissions, an oil control baffle is used that will also be removed. The baffle will be destroyed in the removal process, but the shims are reusable. Attach a dial indicator so the measurement bar rests on the drive-lined end of the output shaft. Then, zero the dial indicator and gently pry up on the input shaft with the pry bar. Note the change in the dial indicator reading as you move the shafts up. Since shims only come in certain thicknesses, the manuals often specify a minimum and maximum measurement. Let's try an example. If the end play measurement is 2/1000ths of an inch, add the minimum and maximum preload measurement from the manual to the existing end play to calculate the combined size of shim and baffle, which would be acceptable. Since preloading the shaft and bearing puts them under pressure when the case is reassembled cold, select a shim and baffle size nearest the minimum measurement to reduce noise. The main shaft of the ZF transmission uses an oil control baffle that is installed with the shim. End play of the counter shaft is controlled by a shim alone. After measuring end play on a ZF transmission, make sure the surfaces are completely clean. Then, fit the new shims and baffle plate beneath the outer race. Now finish assembling the transmission. When finished, check the input and main shafts. They should turn freely by hand. Remember, the adjustments vary depending on the transmission, so follow your shop manual carefully. Don't assume any transmission is the same as another. As an example of another typical transmission adjustment, let's look at end play adjustments, this time using an M50D. Assume you've replaced the output shaft tapered roller bearing. Anytime a major component is replaced that affects the length of the subassembly, you must measure and possibly adjust the end play. To measure end play, use a micrometer and measure 4 different locations on the M50D. The 4 measurements are called dimensions A, B, C, and D in your shop manual. Look at measurements A and B to see how it's done. Dimension A equals the height of the input shaft bearing outer race above the front surface. Dimension B is the depth of the front cover outer race bore. When the depth of the bore is greater than the height of the race, you have end play. If the end play is too great, component damage and premature wear are possible. Basically, you want to add a shim that makes the depth of the bore almost equal to the height of the race. To adjust end play, follow the guidelines outlined in your shop manual. The important thing to remember is that correct end play is essential to make up for case expansion. When reassembling any transmission component, you need to apply sealant to cases, covers, bearing retainers, and many other parts. When applying sealant, be extra careful to apply small and efficient beads. Make sure to use the correct sealant. Silicone sealers are not recommended in some applications. Don't let any drop inside where it can travel in the fluid to clog lubrication holes. Don't put any on the top cover. It can fall in the transmission. And if the sealer squeezes out on the outside of the case, you can assume it's dripping into the transmission on the inside too. Remove the cover or component, clean up the sealant, and start over. Now you're ready to apply sealant to the retaining bolts on the rear of the cover and install them. Then, install the remaining top cover bolts without sealant. Finally, install the drain plug. When it's completely reassembled, be sure to shift the transmission into all gear positions to make sure it works correctly before installing it in the vehicle. Now let's take a look at the S542ZF transmission. It's assembled much differently from the other transmissions we've seen so far. Thermal expansion is required on the ZF because many of its components are attached to the shaft using a shrink fit. A gear heater is the best device to use because you can heat the components evenly. When heating gears, be careful not to exceed the recommended heating times and temperatures listed in the manual. Overheating a component can alter its tempering and cause it to break under load. If you have them, heat sticks that melt at specific temperatures can tell you when the component is hot enough and when it's been overheated. Your shop manual lists all parts that require heating, as well as heating times and temperatures. Inspection and repair procedures for transaxles are very similar to those for transmissions. However, there are some differences. The front-wheel drive transaxle combines a transmission and a differential in a single housing. After disassembly, you'll notice that a significant difference in the transaxle is that it doesn't employ a countershaft. Instead, gears on the input shaft mesh with gears located on an opposing main shaft. End play and preload measurement procedures for the front-wheel drive transaxle are similar to the rear-wheel drive transmission. One of the unique measurements you'll make when reassembling a transaxle is pinion gear backlash in the differential. To measure the backlash of the pinion gears, install the left and right half shafts into the differential and support them on V-blocks. Using a dial indicator, twist the shafts in opposite directions to measure the free play between gears. The readout of the dial indicator should be less than 4 thousandths as specified in the shop manual. If the backlash were not within specification, the differential would be replaced as a unit. Also, be sure to check the differential bearings. If they're serviceable, you can place the differential assembly in the clutch housing and measure for correct bearing preload. Most of the repair procedures for the transmission and the transaxle are similar. Four-wheel drive vehicles add another component to the vehicle's drivetrain, the transfer case. Off-roading introduces the racing driver to an entirely different set of driving conditions. Here, skill and accuracy are clearly more important than sheer speed, and the driver must learn specialized driving techniques to handle the unique characteristics of four-wheel drive vehicles. A four-wheel drive vehicle uses a transfer case to redirect part of the engine's output to the front wheels. Now, while most transfer cases have some similarities to transmissions, they do introduce a few new components and some unique considerations that we'll uncover in this topic. In a manual shift transfer case, such as the Borg-Warner 1356 from a Bronco or F-Series truck, the major operating components are the input shaft and carrier gear, the lock-up shift fork, the drive sprockets and chain, the high-low shift fork and hub, the front output shaft, and the rear output shaft and oil pump. To direct the transmission's output to the front and rear wheels, the transfer case uses a front and rear output shaft. Both have sprocket gears linked by a Morse chain. In two-wheel drive, the input shaft is locked to the rear output shaft, supplying power to the rear axle. The drive sprocket on the rear output shaft freewheels, and no power flows to the front axle. In four-wheel drive, a lock-up collar controlled by the lock-up shift fork assembly slides forward to engage the drive sprocket and shift collar hub, locking the drive sprocket to the rear shaft. The chain then drives the front output shaft, powering the front axle. The second function of the transfer case, gear reduction, is accomplished using a planetary gear assembly driven by the input shaft. When the transfer case is in neutral, the sun gear, planetary gears, and annulus gear all turn freely with the input shaft. In this condition, no power is transmitted to the output shaft. In two-wheel drive and also four-wheel drive high, the reduction hub, controlled by the high-low shift fork, splines the input and output shafts together in direct drive. When shifted into four-wheel drive low, the reduction hub moves in the opposite direction, locking the annulus gear into a fixed position. When the annulus gear can't rotate, the planetary cage which is splined to the output shaft is forced to rotate at a slower rate. A positive pressure oil pump driven by the output shaft provides lubrication to the output shaft components whenever the rear drive shaft is turning. Now that we've identified components and their function, let's look at an actual repair. This 4x4 was towed in because it jumped out of 4 low and started making grinding noises. Now it won't shift at all. During your road test, you discover that the four-wheel drive shift lever is binding between 4 high and 4 low, even with the engine off. With effort, you finally work it into 4 high. Between 4 high and 2 high, it shifts fine. As you drive off in two-wheel drive and you decelerate, there's a pop and the grinding noise starts again. With any four-wheel drive hard shifting or jump-out problem, start by examining the transfer case shift linkage. Check the linkage for binding and improper adjustment. While here, it's a good time to check the fluid condition and level, and to look for any signs of obvious internal wear or damage. In this case, fluid level and condition are acceptable. Transfer case jump out is one symptom of the problem. After any shift component repairs, be sure to properly check and adjust the shift detent plate and retest the vehicle. If that doesn't correct the problem, as in this case, it'll have to go on the bench. The transfer case has been removed from the truck. Its input and output yokes and seals have been removed, as well as the rear bearing retainer. Next, gently pry off the front cover. Use care not to damage the mating surfaces of the magnesium housing. Disassemble and remove the mode shift fork. Then, remove the upper and lower sprockets and chain. Followed by the rear output shaft with the oil pump. Next, take out the high-low shift fork assembly. Now remove the front output shaft. Finally, remove the input shaft and carrier gear assembly. The next step in finding the problem is an inspection of the components. The mode shift fork controls shifting from two-wheel drive to four-wheel drive. It works with the lockup assembly. There are 3 main things to inspect on these 2 sub-assemblies. Inspect the forks for wear and condition. Check the lockup collar for damage. Inspect the hub teeth and snap ring for wear. All these parts look good here. Next, check the sprockets and chain. The sprockets and chain transfer power to the front wheels when four-wheel drive is engaged. When inspecting the sprockets, look at the teeth and check for signs of slipping or wear. Always replace them as a set. Check the chain for slack in general condition. Now, examine the high-low shift fork. The high-low shift fork controls the shifting from four-wheel drive high gear to four-wheel drive low gear. Check the shift fork and plastic insert's general condition. Look for any signs of wear. The nylon insert on this fork has been knocked loose. With one insert missing, the uneven pressure on the reduction hub makes it extremely difficult to shift. When it did go into gear, the missing insert prevented complete engagement, resulting in jump out during deceleration. Not being fully engaged in either gear caused the grinding. After replacing the high-low fork, inspect all remaining components before reassembly. Check the rear output shaft and oil pump. The output shaft powers the drive shaft to the rear wheels. The oil pump and chain lubricate the transfer case components. Check the strainer and oil holes for clogging. Check the oil pump body, spring pins, and the shaft splines for wear or damage. To inspect the input shaft and carrier gear assembly, check the input shaft splines for wear or damage. And check the teeth on the ring gear of the carrier assembly. The contact surfaces should be free of chips or nicks. And inspect the thrust washer for wear. Check for end play of the input shaft. The shaft should have less than 60 thousandths of an inch end play in the carrier assembly. If end play is excessive, jump out problems could occur. Other than the missing high-low shift fork insert, Everything looks good. Begin to reassemble the transfer case by installing the input shaft and carrier gear assembly in the case. Install the high-low shift hub, fork, and rail next, followed by the rear output shaft with the oil pump. After installing the front output shaft through the lower bearing, install the sprockets and chain. Followed by the two-wheel, four-wheel drive lockup assembly. Be sure the orientation is correct because it can be installed backwards. Apply a bead of silicone rubber to the front case and install the rear cover. Now, install the transfer case back in the vehicle and take it on a road test. It's shifting easily now, and it's not jumping out of gear. Replacing the high-low shift fork corrected the problem. Some vehicles are equipped with an electronic shift transfer case. Working with an electronic shift transfer case is basically the same as working with the manual version, except for an externally mounted shift motor. The shift motor is operated by an electronic control module that has self-test capabilities. Inside the transfer case is a magnetic clutch similar to an air conditioning compressor clutch. It spins up the front drive system to vehicle speed in milliseconds. This allows the shift between 2 high and 4 high to be made at normal off-road driving speed. Well, that concludes our tape on transmissions and transfer cases. We hope you've enjoyed it and learned a few things in the process. We've tried to present transmission, transaxle, transfer case noises, and shift concerns in the way you'd see them in your service bay. We hope this tape has helped you in diagnosing and repairing manual transmissions. You may review any sections where you still have questions. Then, keep the tape handy so you can look at it again when new questions come up. A better understanding of transmissions and transfer cases will lead to better service, greater customer satisfaction, and will keep Ford products in the winner's circle.